Welcome to Module 2 for the AIA Structural Exam Preparation video. I'm Dilip Khatri, and today we're going to talk about shear diagrams. In your structural analysis exam, there are several questions which will ask you to draw a shear and a moment diagram. And today we're going to talk about only one of those, which is the shear diagram. So let's first of all understand what we mean by shear. What is the definition of shear? So if we take the example of a block, just take a block of wood, for example, and sitting on a table, and here's the grain of the wood, and I apply a force, and we'll say for right now that this is glued to the table. This block is undergoing a shear force, and that glue that holds that block to the table is undergoing a shear stress. So shear is a force that's applied to a cross-sectional area, and the stress is defined as that force divided by that area. And so the relationship between a shear force and a cross-section is that the two are in the same plane. So when we think of a shear diagram, and we're speaking specifically of a beam, we are graphing the distribution of that shear stress across that diagram. So let's take an example of a very simply supported beam with a concentrated load at the center. And the first step is, and we'll put some numbers on here, we'll say that this is a 10-foot span. We'll say that this is a 100-pound load, and it's equally distributed, so we'll put it at the center at 5 feet. And the load is equally distributed to the two sides, so we have a simply supported span, 10 feet, with the load occurring exactly at the center. The load is equally distributed in this case because the applied load is occurring exactly at the center. And so the reactions are 50 pounds. They're equal to each other. If we were to have the load slightly off center, I'll redraw this diagram, and I'll give you a shortcut on how you can solve this on your own. Here's my load, and right now I'll take the example that I have a general span of L. The distance to the left span, we'll call this reaction A, and we'll call this B. This distance is A, and this distance is B. The equation for the left reaction is the load times the distance ratio between the span and the distance to the right reaction, and vice versa. So when A and B are equal, A equals exactly half of P, and if the distance from P towards A reaction approaches 0, you can see what happens is B approaches L. And so if A were 0, that tells us that A would equal P and B would equal 0. And the same thing would happen on the other side. If B were equal 0, then that would tell us that B would equal P and A would equal 0. So what it tells us is that by looking at this graph and by looking at the position of the load, depending on where that load is, the closer the load moves to the left reaction, the higher that load. The closer the load moves to the right reaction, the higher that load. And so before you even solve any problem mathematically, you can tell just using what I call common sense, the position of the load should tell you what your answers are. And that's very important in structural engineering. It's very important to have a feel for what the answer is before you actually solve the problem. If my load is closer to my support point, then I should be expecting this load to be higher than this. If I don't get that answer, that tells me that something is wrong. The other thing that's useful in solving problems, before we even get to the shear diagram, is to look at the structure and try to imagine how it is deflecting, or what we call the elastic curve. We look at this structure. Let me go back down to this structure over here, the one that we started with, and if I try to draw the elastic curve, which is also called the deflected shape, this structure looks something like this. This structure will look something like this. And that tells us what is happening internally to that structure. So let's go and let's try to draw a shear diagram. And we'll take the simple problem first, and then we'll do something a little bit more complicated. But let's take the simple problem first. Let's start with the simple beam with a load exactly at the center. And we'll use the numbers we had before with the 100 pounds. And we'll place this load exactly in the middle. And we'll make it a 10-foot span with 5 feet to either edge. And the first thing you do when you draw a shear diagram, you extend the lines out. And what you want to do is you want to draw a line essentially at wherever you have your support point and wherever there's a load occurring, because that's going to tell you where something is going on with our shear diagram, where there's going to be a change. So our reaction on the ends is 50 pounds and 50 pounds. The first rule, as we know, sum of the forces in the y direction must equal 0, so the reactions RA plus RB should equal P. And that's where we are able to show that 50 plus 50 equals 100. That tells us that our reactions are correct. So let's do a free body diagram, starting from the left side, moving to the right side. And if we do a free body diagram, we have our support point, we have our beam, and we're going to cut a section of this beam in our free body diagram. And so on the left-hand side, we have the reaction load of 50 pounds. There's a reaction occurring inside the beam, which is a shear force and a moment. I'm not going to worry about the moment for right now. I'm only going to worry about the shear force. And if I sum the forces in the y direction, I have plus 50 plus v equals 0, which tells us that our v is equal to 50 pounds. And the shear force is remaining constant from point A until it reaches the midpoint. So our shear diagram is going to start off here at plus 50, and it's going to remain constant until we reach this concentrated load. And so the rule for the sign convention is the shear is determined by the force on the left-hand side of the shear diagram. Since this force is going positive, we refer to this as positive shear. And many of you have seen this in the books. If we drew a free body diagram of an element, it's the left force. If it's going up, then this is positive shear. If the left force is going down, this is negative shear. What happens at the load point? When we reach the load point, our positive shear of plus 50 is displaced by the load of negative 100 pounds. So the shear diagram drops down to minus 50. And then it remains constant because there's nothing else happening on this span. And when it reaches the right reaction point, we are again back up to plus 50 and it goes back to 0. So the fundamental rule in drawing a shear diagram is you start at 0 and you end at 0. You always have to start at 0 and you always have to end at 0. And so that's your shear diagram for this simply supported beam. Let's take a look at another type of beam. We'll again make it as simply supported. And this time we're going to put a uniform load. A uniform load, referred to as W, is distributed load over a distance. So for example, if my W is 100 pounds per foot, what does that mean? That means that for every foot of distance, I have 100 pounds. This is a uniformly distributed load, called a uniform load. So now again, we draw our lines. We have two reaction points. We have RA, we have RB. We draw our lines down. We draw our horizontal axis. And first thing we have to do is compute the reactions. Let's also put a span on here. We'll make L equal to 10 feet. We'll make W 100 pounds per foot. The total load, I'll call it P, the total load is equal to the uniform load times the length, W times L. And W is 100 pounds per foot times 10 feet. So we have 100 times 10, so the total load is 1,000 pounds. And because the load is uniformly distributed, we immediately know, because it's perfectly balanced, that the two reactions are equal to each other on this simple example. So RA will equal the total load divided by 2, or WL over 2, or 500 pounds. And RB will equal RA, or 500 pounds. Now when it comes to drawing the shear diagram, we're going to start with the left reaction. We're going to go up positive plus 500. And remember, we know that we have to always end up at 0. Let's do a free body diagram of this beam and understand what the equation of the shear diagram looks like. So if we do a free body diagram, we're going to cut a section of this beam. And we're going to start from the left-hand side. We know our reaction is 500 pounds, but we have a uniform load which is W equal to 100 pounds per foot. And we have some reaction here, V, which is the shear in the beam. This is an internal force. This is an external force. This is an external force. And this is an internal force. And we will say that this is occurring at some distance x. So we follow the basic rules of structural analysis. Sum of the forces in the y direction must equal 0. So let's sum the forces. We have plus RA, because this is going up, it's positive, so this is a positive force, minus the downward force, because W is going down. And although it should be quite obvious, but I'll go ahead and draw a coordinate system on here. This is y, and this is x. So we have plus RA, because this force is going up, minus W times x, and then plus V equals 0. So V is equal to And for right now, I'll keep the sign convention. I'll keep this positive, RA minus WX, because whether it's plus or minus will come out from these numbers. So what is RA? RA is 500 minus 100 times X equals V. As long as this is positive, the shear diagram will remain positive. But what does this equation tells us? It tells us that this is a linear diagram because this is the equation for a straight line. And so at some point the shear will equal 0. In order to find out where the shear is equal 0, we set the equation equal to 0 and we solve for X. And if we do that, we have 500 equals 100X, which tells us that X is equal to 5 feet. At X equals 5 feet, our shear is 0. So going back to our diagram, that tells us that at the mid span, here our shear is 0, and it's a straight line. So the shear diagram looks like that. This is positive shear, this is negative shear, and it ends up down here at minus 500. And the reaction here is plus 500, so it goes back up to 0. And you can see that in this equation, if you plug in V equals 500 minus 100 times X, and let's make X equal to 10 feet, it ends up at minus 500, which is exactly what the shear diagram shows. So whenever you have a uniform load, you're going to have a linear shear diagram. Let's take a look at another example. Let's take a look at an example of a cantilever beam. So a cantilever beam is a fixed support beam which has a load on the end. We'll make this a very simple example. So here again we have a load on the end. We have a certain span. And on this support point here, this is a fixed point. We have an end reaction and we have a moment because it's moment resisting. So it's resisting rotation. And so right away, we already know that the end shear here is going to equal P plus P because this P is going down, and the moment, which we'll talk about in the next segment, is actually equal to P times L, but we'll talk about this separately. The shear diagram for this is really quite simple. If we do a free body diagram, we graph the shear. We're going to start off here at plus P. It remains constant because there's nothing else going on inside the beam. There's no other load, and then it drops down to 0. And that's our shear diagram. If I wanted to make this a little bit more complicated, I could add a uniform load on here. And then what would happen? Then our end reaction, V, becomes P plus, and let's make this W, WL. Let's attach some numbers to this. Let's make P 100 pounds. Let's make L 10 feet. Let's make W 100 pounds per foot. What would our shear be? Our shear would equal our same as our reaction. It would equal P 100 pounds plus W 100 pounds per foot times 10 feet. So it would equal 100 plus 1,000, which would equal 1,100 pounds in my second example when I add the uniform load. What happens to the shear diagram? I'm still going to start off up here with plus P plus WL, except that now this becomes 1,100 pounds, but now this curve is going to change, because now we have a uniform load with a concentrated load. Let's take a look at that. Let's take a look at that and let's redraw that sketch. So we have a uniform load, 100 pounds per foot, and we have an end concentrated load of 100 pounds. So we have, how does our shear diagram look? Well, we're going to start with plus 1100, and we have to end at 0. And so what happens? This is a linear diagram. So let's do the free body diagram. Let's graph this beam. We're going to make a cut, and we have our load. We're starting off here with our reaction. We have a shear load here, and this is measured as a distance x. So this end reaction V is equal to 1100, and this is W. So the equation, which again, sum of the forces in the y direction equal to 0, we have plus V minus W times x. Actually, let's change the notation here. Let's make this plus P minus Wx equals V. So we have plus 1100 minus 100x equals our shear. What's going to happen, this is a linear diagram, is your shear diagram is going to look like this. It's going to be a linear diagram, and then when it reaches here, this will be at 100, and then it will drop to 0. And the way we can see that, we can plug in the distance 1100 minus 100 times 10 feet, which is 1100 minus 1000 equals 100 pounds. That's at V equals, at X equals 10 feet, and then at this point we have the 100 that then drops it down to 0. And so that's our shear diagram. So those are 4 examples for you, and this will bring us to the end of Module 2, and in the next module we'll talk about moment diagrams. Thank you.